So we've heard about fast storage, we've heard about fast networks, so naturally the next talk is going to be about fast processors. So the quote here is from Steve Oberlin. So Steve Oberlin is now the CTO of NVIDIA, and previously he is one of some of the achievements in the past have been the chief architect on the Cray T3D and T3E systems. So he has a pretty good pedigree in terms of high performance computing. And the message that I want to put over here is that accelerated computing is not the same as an x86 or standard CPU, but a bit faster, but actually something rather different. And if you want to get the best out of a GPU, then you need to start thinking differently about your applications and start applying some different methodologies and techniques to your applications so that you can get the best out of the parallel processing. But let's think first of all about what sort of problem that you as application developers are facing, and in fact it's a reciprocal problem in the sense that, or symmetrical problem in the sense that it's a problem that all of the silicon manufacturers have to face. It doesn't matter whether you're NVIDIA or AMD or Intel or IBM or ARM, we all have exactly the same sorts of problems because our problems are faced by us are restricted by the laws of physics. And the laws of physics, among other things, are making the scaling laws of semiconductor manufacturing that we rode on for many years, from the 1990s onwards. The increase in performance, not single-threaded performance, by the way, the increase in performance was rather predictable. If you were working for a processor manufacturer in those years and you are asked to give a roadmap, you could simply put your ruler on that line and project forward and tell your customer what the performance of next year's chip was going to be. Those days have long finished. They finished several years ago, or in about 2004. Dennard scaling, which is the thing that was allowing us to increase the frequency of transistors and frequency conflicts of transistors within a fixed power envelope. All of those things went away in about 2004. And as a consequence now, the increase in performance of cores in CPUs is rather incremental, rather slow. All the good ideas have been used up by now. And indeed, there isn't much prospect of things getting any better. So if you buy a large CPU system today, in 5 years' time, you're not going to see that much difference. So there's a physics problem. There's also an economics problem. So this is data from CERN Open Lab. NVIDIA is not even a member of Open Lab, so this is not something we might have influenced in any way. And what they plotted here is the price-performance ratio of one of the benchmarks CERN uses for evaluating machines. And for a long time, the price-performance ratio improved, flattened out a bit, and there was a period here, just in the recent years, when the price-performance ratio went in the wrong direction. So actually, for a fixed performance, you were having to pay more money. Mostly in that case, that was due to the increase in the price of RAM. Now, the people who made that chart, which I insist were not NVIDIA, very kindly put some predictions on here on how they thought that GPUs would be able to influence that price-performance graph. And what I want to do in the remainder of this presentation is talk about how we think at NVIDIA that you can get onto that curve and the sorts of things that you as application developers have to do to get there. So there is a sense of urgency, I think, now. The laws of physics stop evolution of processor performance. Moore's law, whilst not being completely out of steam, is certainly slowing down, and you'll see that the time interval between increments on the nodes of semiconductor manufacturing is increasing, and it's getting, we as semiconductor manufacturers know it's getting more and more difficult to manufacture these wafers. So Dennard scaling, the frequency scaling is going, the number of transistors is reducing, economics is getting worse, the price you pay per transistor is tending to go up now, and they don't get any faster. So the question to the community now is, what is going to be your plan to address this situation? Unsurprisingly, as a representative of NVIDIA, unsurprising, my answer is going to be that you should use GPUs for your scientific simulations. But not just GPUs in the sense of take your old application and port it onto a GPU, but start thinking in a different way about how you are going to create applications for this new class of parallel processor. And I got to back this graph, this green line up with some data right at the end of the presentation. So this is not a pure. This has a whiff of marketing about it, but it's not a pure marketing slide. I do have some data later on. And the issue is that you really need to be thinking about all layers in this stack that will lead to your applications. You need to be thinking about the architecture and the parallelism within your system. You need to be thinking about how you can put systems together. We have our good friends from HPE here, and Atos, and I hope I haven't put anyone if I've forgotten someone, but there'll be maybe other system vendors in the room as well. You need to think, in particular, this community needs to think about the algorithms that you're developing. Can you develop new algorithms that fit better onto the new classes of processors that you're going to have given to you, well, sold to you, of course, but not given to you, but your funding agencies will give them to you, and when you've got the right algorithms, you can write the right applications. And there are going to be, I think, 4 aspects to the things that you need to think about. First of all, there is the accelerated computing model, where you have a CPU and a GPU, different classes of processors in your system, with those different processors being appropriate for different aspects of your algorithm. Some parts of your algorithm may be less parallel and latency sensitive and will fit well to the traditional CPU. Some parts of your algorithm may be highly parallel and throughput sensitive and bandwidth sensitive, and therefore should run on a high bandwidth throughput processor. The second thing that we are seeing, and this is something that's already tangible, is the application of AI in the world of scientific computing. And I'll show you some examples of this. But essentially, one of the ideas is to take a detailed algorithmic solution of some equations. Cloud modeling in weather forecasting is a good example of this. Replace that complex, detailed, full physical simulation with a neural network that behaves in the same way as the output from your numerical simulation. And that's the sort of speed up that can deliver those very large speed ups that I showed you on that green graph. The third thing is about precision of your arithmetic. Traditionally, this community has worked in FP64 precision, maybe even quad precision occasionally. I'm not sure the sorts of things you might be doing. But one of the ways that you can drive forward performance is by computing in reduced precision, because that reduces the amount of energy you have to put into moving data around and increases the speed at which you can do computations. And there are certainly applications in which some of the computations can be done in a reduced precision arithmetic. And there's finally this idea that I mentioned at the beginning of the talk, earlier on in the talk, that you should be thinking about the whole picture, not just your little piece of the story. NVIDIA delivers a complete platform for doing numerical simulations and AI, of course. At the lowest level, we have the GPUs and their architecture and all the tools and libraries that you need. We work with all of our partners to create solutions that can be delivered to the end users, both physically and in the form of cloud. We provide all of the tools, libraries, AI frameworks, everything that you need to be able to develop your applications. It's taken NVIDIA a decade to build up this complete ecosystem. And without this complete ecosystem, GPUs have little value. There's a little value to a processor in isolation. What's needed is a complete ecosystem that can be used by application developers. And there are essentially 2 goals that we're always aiming at with this ecosystem, with all of this CUDA platform. One is for the geeks, and I assume that geeks covers most people in this room. For the geeks, how can you get close to the optimum performance of the device? But there are plenty of other people who are down here, they want to get a reasonable performance for a modest effort. And so we make it feasible to get the optimal performance, but also not too much effort to get the acceptable and decent amount of performance out of the application. AI, artificial intelligence, of course, is the flavor of the month and the year and maybe even the decade. And there are lots of high-profile examples that are in the popular press. But of course, what this community might be more interested in is things like the SKA or the CERN or ITER that are producing far too much data to be analysed by humans, and therefore an AI approach can be useful for analysing this vast amount of data coming out of those experiments. Reduced precision. So we have now, this is an interesting one, this is a plot of a graph of one of the routines from Jack Dongarra in LAPAC, I think it is. It's an iterative solver. And in a simple FP64 implementation, you'd see this sort of performance curve. The way he achieved this was to do the early iterations of the solver in a very much reduced precision, and gradually increase the precision as you came towards convergence and try to drive down the residual. And you can see actually the performance here is actually higher than the rated performance of the device itself. Plasma fusion application that was using FP64, and an earthquake simulation that was also using reduced precision. So what I'm asking you to do is to start thinking about how you can align your application development towards what's being presented to you. This is the traditional way. Ride the wave that the processor manufacturers are offering you, and you will get incremental improvements. I'm sure there's still a few more good ideas. Intel and AMD and ARM employ smart people. I'm sure they've still got a few more ideas up their sleeve.
Using more than one core.
If you're going to go parallel, use the best parallel processor. Follow the platform improvements. We have our system friends in the room who can provide good platforms with plenty of GPUs in them. Think about how the application can be parallelized. How can you think about data locality? Flops essentially are free of charge these days, but moving data around is extremely expensive. And think about new algorithms. Think about artificial intelligence. Think about data science. So I promised some actual figures, some actual graphs rather than a marketing graph. Luckily, none of these, maybe I'm not sure what GTC is actually, but maybe these are chemistry applications, so I'm not going to upset anyone by showing an application, their favorite application or their least favorite application. Amber, which is a molecular dynamics code, is a particularly good example of what I've been talking about. Whenever a new hardware feature is added to a GPU, the Amber developers latch onto it and think, how can we apply this new hardware feature into our application? And you can see here that the slope of improvement of the performance of the application is very different from the slope of the improvement with CPUs, where they're simply relying on the incremental improvements of manufacturing and some new microarchitectural ideas. And so the proof is in the pudding. The Gordon Bell Prize is the annual prize for who has the best, makes the best use of supercomputing for their application. And 5 out of the 6 finalists this year were using GPUs, and we're using the sorts of ideas that I put forward in this presentation of AI to help replacing computation with AI, using reduced precision, and using large numbers of GPUs in the simulation. So I hope this will stimulate you down what we believe, of course, is the right path for the future of your application.